Welcome back. In this video, we're going to discuss the cosine formula for the dot product. In the previous two videos, we discussed the Pythagorean theorem and the law of cosines in order to allow us to get to a place where we can see where the cosine formula comes from. Recall from our previous discussions that the dot product had two main functionalities, one of which was to measure the parallelity between two vectors. The other one was to enable us to project one vector onto the direction of another vector. Each of these functionalities has different mathematical tools associated with it. In this video, we're going to focus on the main formula or the main theorem that allows us to interpret the dot product as a measurement of parallelity, which is called the cosine formula for the dot product. In future videos, we'll really derive a projection formula using the dot product and then show how to use it in action. With that stated, I think we should actually just state the cosine formula for the dot product. And we're going to state this in general space. So let x and y be an element of Rn. And you might say that n is equal to 2, 3, so it could be R2, it could be R3. Later in life, this could be 4, 5, 6. This holds in general. To see more about that, you would take a linear algebra class. Yay! Then we say in the cosine formula that x dot y, and we could tell that's a dot because the left and right sides of the dot there are vectors and they're of the same size. This dot product is equal to the 2 norm of x times the 2 norm of y times the cosine of theta, where theta is the angle between x and y. We're going to get into the interpretation of how to read this. For now, I wanted to show where this comes from by doing a little bit of analysis using geometry. So you might call this a proof. You could also call it a derivation if you started with it and then stated the theorem. So let's visualize x and y in Rn having the same initial point. Because I haven't said what the initial point is, we of course assume that that initial point is 0. In this visualization, we're going to do something quite amazing. We're going to assume that we're looking at vectors in R3, R2, R4, and we're looking at the plane that these two vectors sit in. Later in life, you'll see that two vectors that do not point in the same direction, if you take any scalar multiples of the vectors, they form a plane. So we're looking perpendicularly down onto the plane that those vectors live in. If we remember about the triangle law, and we take the connection between the terminal point of y and the terminal point of x, and then maybe we go from y to x. So we go along y, and then we add this vector, and we get x. If you'll remember, this vector would be x minus y. And the way that you can confirm this for yourself is if you add y to x minus y, so that's y plus x minus y, the negative y and y cancel out, and you're left with x, which is this vector. As you see here, we now have a triangle. And this triangle, if we think about this as the angle theta, this triangle immediately gives rise to the law of cosines. From the law of cosines, we know, what do we know from the law of cosines? We know that the length of the side across from theta, well, the length of that side would be the 2 norm of that difference. And of course, in the law of cosines, we said we squared it. And let me just make a specific connection between the notation we used in the law of cosines and the notation we're using in this video. Because each of these should be lengths, of course, we're going to go ahead and write their 2 norms, because that's what 2 norms are designed to do, measure lengths. Here we write the 2 norm of x, and here's a. And the law of cosines said that c squared was equal to a squared plus b squared minus 2ab times the cosine of theta. Well, here we go. We know that c squared is equal to a squared plus b squared minus 2 times a times b. Oh my God, and I'm running out of room like a rookie. Oh, do you see that? Times the cosine of theta. Oh, I'm really disappointed with myself on that. Okay, so by the law of cosines, we see that we could write the norms of this triangle related to each other by this equation. But we also have some algebraic properties of dot products, one of which stated that if I take the 2 norm squared, that's equivalent to taking the dot product of the vector inside the 2 norm with itself. So that was, I think, algebraic property number 2 or 3, I forget the number right now. But the way that you might see this is that if I take the 2 norm of u squared, this is u dotted with u. That's a quick reminder. Furthermore, we know by bilinearity, this is dot product over subtraction, and I can distribute this. So this would be x dot, and maybe I do this in 2 steps. So this is left distributivity. I'm distributing it over the left. And then I have right distributivity because I'm going to distribute over the right. So this is x dot x minus x dot y minus y dot x. And of course, minus times a minus is a plus in scalar world. And then we're left with y dot y. We have a further realization that x dot x is the 2 norm of x squared. That's by the same property that we used up here in reverse. We know that the dot product is symmetric, which means that this is actually 2 copies of x dot y, and then this is the 2 norm of y squared. And notice that we actually have 2 equations where one side of both equations are equal. A mathematician would say by the transitive property of the equation relation, which means if A equals B and A equals C, then it must be true that B equals C, right? In other words, I should be able to set this right up here that came from the law of cosines to this, which came from the algebraic property. So let's go ahead and do that. I'm going to need a little bit more space. By the transitive property of equality. And the way that you could think about this if you're a normal person is, if you know that A is equal to B and A is equal to C, then you can immediately conclude that B is equal to C, right? And that's, again, we said that, right? Here you've got this equal to that. You have the same exact thing equal to some other thing. It means those 2 things are equal. Let's go ahead and compress this a little bit. We see, so these 2 things are equal. So we see that the 2 norm of x squared minus 2x dot y plus the 2 norm of y squared. And I don't have enough room to write this because I write really big using these felt pens. So I'm going to go ahead and copy this under. If you're writing in your notebook and you can write a little smaller, I would recommend doing this in 1 line just to make it easier to read. But I also want to make it legible for those video watchers that are using smartphones. That's why I like to write big. So here you got 2x y in 2 norms cosine of theta. And now you have an equation with similar things, similar expressions on both sides. In fact, on both sides we have the 2 norm of x squared. So we can subtract on one side, since those are both scalar multiples. Those go away. So literally, by subtracting from both sides, those go away. These go away. And then they're left with negative 2x dot y equal negative 2 times the 2 norm of x times the 2 norm of y times the cosine of theta. And we can divide both sides by negative 2. And we see this is the exact cosine formula that we claimed was true at the beginning. This concludes our proof of the cosine formula for the dot product. One note I should make is that this proof holds only when theta is not equal to 0 and not equal to pi. In those cases, we actually have a different proof, which you can find in the handwritten lecture notes. In the next video, we'll take a look at some examples so that we can interpret what this formula means in geometric intuition. See you there.